The Rotor Ride is a typical amusement park ride that moves in a circle. Generally, it would rotate with some angular velocity omega, and the riders actually ride standing upright against the wall, something like this, which means that each individual rider has a tangential velocity v that would be calculated by doing omega times r, where r would be the radial distance they are from the center out like this. From the aerial view, we can see the action of the ride, right? We see that it spins with centripetal acceleration at some tangential velocity. Now, obviously, it ramps up to that from zero, but from this perspective, it's very hard to see the forces at play. So if we cut this in half and rotate it 90 degrees on the x-axis, in other words, rotate it so we're looking at it from the side, then this person would appear as though they are standing against the wall like this with the floor underneath them. And the idea of the ride is that this velocity, or this angular velocity, increases to a point where eventually this person feels as though they are stuck to the wall. Now, that's not actually what happens, but we'll go through the forces in just a moment. But what is possible is that eventually they do experience such a force that the floor itself can move out from underneath and the person does not move. So they experience a vertical acceleration of zero. So what we have to recognize is the relationship between this diagram and the forces at play and this diagram. So we're going to assume that this is already moving fast enough such that the floor could drop out and the person is suspended against the wall. If this is true, we know that the forces acting on the person, of course, are weight, F of g, and then the wall itself is behind them. This tangential velocity is causing the person to want to leave the circle. This wall is preventing them from leaving the circle, so you can imagine that they are pushing on the wall this direction, which means that the wall is pushing on them this direction. Now, contact with the wall perpendicular is a normal force, so this is F of n. And now the key component of this diagram is that F of n creates a contact between the wall. And so F of g is supported by the fact that it's pulling down and this person would slide against the wall. So a resistance to that motion would be friction force, which would act up. And in this case, the friction force, F of f, as always, is calculated by mu times F of n. And so we see the relationship between the friction force and the normal force. But we have to analyze this diagram in conjunction with this diagram to really recognize what F of n is. Because obviously, in order for the acceleration in the vertical direction to be zero, F of f must balance F of g. And so a conclusion here is that in order for balance, the sum of the forces in the vertical direction must equal zero. So therefore, F of f minus F of g equals zero, and the magnitude of F of f must be m times g. And so we know what the value, the magnitude of F of f is, but we don't know what F of n is. And so we have to go back and look at this circle to really make sense of that. This normal force in this diagram over here can still be depicted from this person along the central axis towards the middle. F of n is pointing towards the centripetal center, which means that in terms of the summation of the forces centripetally, F of n is an unbalanced force. There is no force pushing outward, right? Although it feels as though there is to the rider. Remember that that feeling is simply the inertia of the momentum causing you to want to fly off the ride. And so as you go to fly off, the wall pushes against you, which prevents you from falling off. That gives you the impression of being stuck to the wall, but you're not, right? You're actually being thrown against it with some velocity. Nevertheless, the centripetal force is the normal force, and the normal force can then be calculated as m times ac. And so we see that F of n is equal to m times v squared over r, where this velocity is this tangential velocity here. And so this allows us to take F of n and substitute into the f of f formula. And based on the fact that f of f must balance f of mg, we can work backwards to calculate a number of things. So if we finalize this relationship based on our f of f formula, we would say f of f equals mu times f of n, and then we take these two things that we've derived through the summation of the vertical forces and the summation of the horizontal, which also happens to be the centripetal forces, in order to come up with the fact that mass times gravity is equal to mu times mass times v squared over r. And the first thing that we notice is that m cancels on both sides. And this should make sense. Amusement park rides are often built in such a way that the rider's mass does not matter. And so as long as the coefficient of friction of the surface is a high enough value, we can describe the velocity necessary at a given size of a ride in order to stay stuck against the wall. In other words, v would be the square root of g times r divided by mu.